Okay, now we will start from a simple example of dice. That's the simplest possible example in statistics. So we are going to consider this way. So previously, in the previous chapters, when we learned like chapter 1, 2, 3, 4, 5, 6, like the rolling one dice is one experiment. And you can repeat that. Like either you can throw like 100 dice at a time or throw one dice 100 times. We consider them as the same repetitions of 100 experiments. But now, like you can think it this way, like if you throw 100 dice at a time, you can think it as one experiment. And if you repeat, that means just pick up all the 100 dice again and throw them again. That's one repetition. And then collect them again, throw them again. That's another repetition. So there is no problem in doing that. So let's start from 2 dice. Simplest case. So you are throwing 2 dice. Then you know it is just one experiment, even though there are 2 observations. But actually, in the end, you will record only one number, which is the average of the 2 dice, right? So when you throw 2 dice and calculate their average and repeat that again. And suppose that if you repeat the experiment of throwing 2 dice again, if you repeat the experiment of throwing 2 dice at the same time, and then what is the probability that how many times you are going to get the average of 6? So how many times you can get the average of those 2 dice equal to 6? So it's pretty simple algebra. It's like a brain teaser IQ test. Try this. Simply speaking, to have an average of 6, that means both dice must be 6, obviously, right? So 6, because 7 is not available, like so 6 plus 6 divided by 2 is the only possible case out of 36 possible scenarios. So when you throw 2 dice, there are 6 times 6 number of cases, but only one of them satisfy this event. That is, the answer is 1 over 36, right? If you list all the possible outcomes, 36 outcomes, and obviously they are equally likely, and only one case of 36 is what you want, is the event you want to see that. So in a similar way, you can calculate the probability distribution for X bar, not for 6, but for like 5.5. What is the probability of getting 5.5 average? This happens when one dice has 6 and the other has 5. And remember, you have to think 2 cases, 5 and 6 or 6 and 5. There are 2 different cases out of 36 cases. So the probability is like this. In this way, you can calculate the probability of X bar equals to 5, 4.5, 4, 3.5, up to 1. So all the probabilities can be calculated with a very simple, just by counting cases. It's pretty simple. And then let's see. We know this is the distribution from one dice. When you throw a single dice, and if you repeat that, then you will get a uniform distribution. But when you throw 2 dice at the same time, then it starts to be different. Like as I said, this is 1 over 36, and this is 2 over 36, right? In that way, you can calculate probability for each of them. And it is now different because you are throwing two dice and calculating their average. So already when your large scale experiment is only two, still it's different from the original one, single one. That's the sampling distribution. So this is the sampling distribution of the average from throwing two dice at the same time. And then, as I said, it is different, but it is related. It's related, so we will study the relationship later. And now, you may increase the scale of the experiment. Not just throwing two dice at a time, but let's throw five dice at a time, for example. Then I can calculate the probability on computer. I did, and this is the probability. So there is actually some probability at 6 for excuse me. So what we do here is you throw 5 dice at a time and record their average, right? Just calculate the average of 5 numbers and only keep the average and repeat. Repetition is collect 5 dice, throw them, and calculate the average of them. Keep that. Keep the average only. That's one repetition, one iteration. So, based on that experiment, we can calculate the distribution, and the probability of 6 is actually not 0. It looks like 0, but actually there is a small probability, which is so for the average to be 6, all the 5 dice must be 6. So that is 1 over 6 must be multiplied 5 times, right? Which is a very small probability, so it looks like 0 here. Okay, then you may increase the number to 25. Then it looks like this. Of course, there is a probability at 6. Now it is the probability equals 1 over 6 times 1 over 6 is multiplied 25 times. So 1 over 6 to the exponent of 25, which is super small, very close to 0, and even up to this point it looks like 0, but actually not. There is small probability in these extreme values. So when all the dice keep coming up 6, if that's unlikely but mathematically possible. So there must be some probability here. And so what you need to see from here is that now the shape of the distribution is quite different from the original one. Originally, we came from here. When you have one dice, this was the distribution. But as you increase the scale of an experiment, suddenly it looks quite different. And as you may know, as you may have noticed, it's normal distribution. Looks like a normal distribution. That's why normal distribution is called normal, right? Okay. Now we are going to then I said any distribution converges to the normal distribution. So, but you may think, oh, this dice example is too simple, too nice. It's of course dice is like uniform, which behaves really well. So I'm going to show you what happens if you consider a very strange and unfair dice. Now, let's consider suppose that there is a dice which is strange. I don't know how it looks like, what it looks like, but somehow its probability for 1 is twice larger than the other outcomes. So it's unfair dice, right? So one probability of 1 is particularly large and do the same simulation, experiment. Like in this graph, so this is for single dice, and in the upper right graph, it is the simulation result when you throw 5 dice at a time. Throw 5 dice, calculate the average, and record the average. Then if you repeat that, the distribution looks like this. And if you increase the number of dice to 25, it looks like a normal distribution, right? Still, as I said, there is some probability here. There are probability in like everywhere between 1 and 6, but just still it looks pretty smooth and normal. And let's think about another strange dice where 1 to 3 are twice more likely than the others. If you can imagine, if you can make this dice and throw five of them at the same time, then you will get this distribution when you have 5 of this such dice. And when you increase the scale of the experiment to 25, then it again looks like a normal distribution. So, right? And another dice. Now, in this dice, the probability of the outcome is proportional to the outcome. So 6 is 6 times more likely than 1. 2 is twice more likely than 1. And if you could make these dice and throw 5 such dice at the same time, you will get this distribution. And when you have 25 dice, you will get this distribution. So there is a certain pattern. That's the theory. That's the theory for the sampling distribution. You know, we will we will extract these 3 patterns and we will make them formula. Pattern number 1, the expectation of the average is actually the same as the original average. So let's see here. So in this case, the center is slightly above 4, between 4 and 5, and between 4 and 5. That's the mean. Mean is here because larger values have more probability. So its expectation must be somewhere between 4 and 5. In earlier examples, like let's come back here. In this case it's symmetric. So the mean is always 3.5. Always it's centered around, symmetric about 3.5. Even if the size increases, right? And in this case, mean is actually lower than before because lower side has more probability. So the mean is 3, slightly above 3 or very close to 3. It does not change. So if you compare 5 and 25, their center, their peak are the same. That is pattern number 1. In any case, the location of the peak changes across colors, but between the bottom and the top, they are the same, always the same. And pattern number 2. As the scale of the experiment increases, the variability decreases, which means the shape of the graph is more concentrated around small range. So it becomes more like a spark at a point. That's clear in all cases, some extreme values become very extremely unlikely. So the probability here are kind of gone. They are nearly 0. And pattern 3, they look like normal distribution. Or mean is so. So then you see what we are going to do. Remember, and you know the conclusion. Spoiler. You know the spoiler. like they are converging to some normal distribution. And normal distribution is parameterized by the mean and the variance. And then pattern 1 is about the mean. Pattern 2 is about the variance. Pattern 3 is about the normal distribution. Combining all three of them, you know everything. That's how the story goes. Okay. Um, okay, then I am going to give you a more clear formulated results in the next video. So, and actually the results are pretty simple, like it's super powerful and useful. The most important theorem in statistics is coming up in the next video. I'll see you there. Bye.